I challenged myself to put my engineering problem-solving skills to the test. No better way to do this than with a mechatronics project. Just like that, I decided to build a drone from scratch, build with 3D printed and off-the-shelf components. Initially, I thought it would be a simple project for my YouTube channel. I could work on this during my spare time after work. It should only take a few months, right? Oh, how was I wrong? Murphy's Law strikes again. Several months turned into several years, many ups and downs, feelings of whether I should quit or dedicate my time to other more important things. Multiple design iterations, countless broken hardware, electrical shorts. Yet one question remained. Was this all worth it? Stick around and I will show you my painstaking yet rewarding adventure towards building a functional drone. And you can be the judge. If you've ever flown a drone, you know how noisy they can be. When I started the project, I lived in a quiet apartment complex with neighbors in all directions. I needed a dedicated space to build and test my ideas without annoying anyone. So I rented a separate garage space within my apartment complex. I signed the papers and got straight to work. First order of business was to purchase a large FDM 3D printer to print my designs. I bought an Atom Labs 3D printer for about $300, got it up and running in less than an hour. I was feeling excited after this successful Einstein print. Shout out to Thingiverse. My requirements for this project are simple. I want the motor distances to span around 12 inches and for this to not be a mini drone. Also, I would like for it to fly for about 20 minutes. A GoPro mount in the front would be a great idea for capturing aerial shots. Last, I want most of the parts to be readily available off the shelf from either Amazon or McMaster-Carr. With the requirements now set, it's time to get to work. I spent a few weeks researching and calculating the types of batteries, BLDC motors, ESCs, and propellers that I would need to use for this project. I ended up with the following specifications. The first item I purchased was the BLDC motors and ESCs. I was eager to get the motors to spin. After uploading the sketch to the Arduino Uno, it was now the moment of truth. And that was not what I was expecting. After troubleshooting for what felt like an eternity, it turns out that all I had was a simple wiring issue. I fixed it. Now let's try again. It worked! Incremental progress. This is a great step forward, but now let's try to step it up a notch and try to vary the speed of the motor with a potentiometer. After coding the potentiometer as an analog input and rescaling the values to the ESC pulse widths, minimums and maximums, I fired it up and drum roll please. We finally achieved the motor speed control. Throughout this project, I encountered many mechanical, electrical, and programming issues that forced me to learn and improve my overall problem-solving skills. For the mechanical issues, the most notable were that of material selection, connection design, and fastening methods. For the material selection, I noticed that the motor-to-frame supports were displacing due to the large thrust forces from the motors. I needed to reduce displacements if I had any hopes of stabilizing my drone. I found these awesome carbon fiber rods on Amazon for a great price. I replaced the 3D arm supports with the carbon fiber rods that I cut to length using a circular saw. This modification had significant improvements on the drone stability because it minimized arm displacements and reduced overall vibrations. For the connection designs, I attempted to fasten the carbon fiber rod to the supports and base by using a thread and nut design. This design is similar to how tap handles grip taps. No matter how much torque I applied to the nut, the carbon fiber rod would just continually slip out of alignment. This slippage poses a huge issue as it can misalign the propeller thrust forces and cause overall instability and overall poor flight performance. Any small amount of force would cause these connection designs to slip. Therefore, I referred to using epoxy to bond the carbon fiber rods to the main chassis. This solution worked incredibly well. The only caveat is the 24-hour epoxy cure time. Not to mention the smell it leaves behind and the mess that you create if you aren't careful applying the epoxy is extremely annoying. For the electrical portion, the most notable issues were that related to the messy wires, electronic speed controllers burning up, blowing capacitors, and constantly waiting for the battery to recharge before retesting. To reduce the rat's nest, I decided to learn how to manufacture my own PCB using KiCad. I learned a lot from Shawn Hymel's PCB series at DigiKey. The link is in the description below. After watching the whole series and tinkering for a few weeks, I finally had a board design that looked worthy of machining. I submitted my order to JLC PCB. Nope, this is not a sponsored video, at least not yet. After 5 days of waiting, I received my PCBs. I soldered and assembled the PCB, which was way better than using the rat's nest prototype board as before. For the electronic speed controllers burning out, I noticed this would often occur when I selected a high derivative term during PID tuning. Since the angle command data has latency and is subject to noise from the IMU, I would see drastic spikes in the motor pulse commands. As a result, this would cause the capacitors to heat up and burn out. So I therefore used smaller values for the D gain and sometimes opting out of it completely. So PID tuning can take a very long time, often days depending on your system's complexity. What can occur during testing with a battery is that the voltage tends to drop the more and more you use it. This voltage drop could affect your selection of PID constants, which leads to unrealistic results. To mitigate this issue, I soldered and created my own custom cable that connected my drone to my power supply, which provided a constant source of power. This drastically helped reduce PID tuning times and the overall amount of time waiting for the battery to fully recharge. For the programming, the most notable issues were that of having to frequently upload program updates when fine-tuning the PID. Also, low sample rates for PID outputs led to constant unstable hovers, and also relying on a single PID plant to stabilize flight led to poor flight performance. I originally used an Arduino Uno for my first drone prototype, as I had the most experience with this microcontroller back in college. I replaced the Uno with the Nano shortly after. The Nano had the perfect form factor, but once I started PID testing and fine-tuning the flight settings, I quickly realized that I would need Wi-Fi. The problem was that every time I wanted to modify and test a different PID value, I would have to re-upload the sketch to the Nano, which would take about 40 seconds to upload. If any of you have ever tuned a PID controller, you know how this program upload delay makes it near impossible to efficiently find optimal PID constants. For instance, if I wanted to modify the p-value from 1 to 3, I would have to type it in the code and re-upload it to the microcontroller, taking 40 seconds to upload each time I wanted to make a change. The PID tuning process requires a lot of trial and error to find the combination of settings which lead to good flight performance. There are other techniques involving math, such as the Ziegler-Nichols method, but those didn't work for this scenario. I did successfully use the Ziegler-Nichols method in my controls lab project, but I wouldn't completely discard it if you're needing a starting point. To combat the upload time inefficiency, I decided to build a web-based dashboard that I could use to send the PID values over WebSocket commands to the microcontroller in real time. The problem is that I would have to further add hardware, PCB redesigns, and programming complexity to the circuit, and I just didn't want to commit that time and energy. I searched for alternative microcontrollers until I stumbled upon the ESP32, which has embedded Bluetooth and Wi-Fi functionality. This is a perfect fit for my drone. After researching for several weeks, I found a great YouTube channel and blog by Random Nerd Tutorials, link in the description below, which inspired and taught me to spin off my own version of the dashboard that I use to update and send the PID settings in real time. This dramatically improved the overall PID tuning and testing process, so thank you very much. The longest part of this whole project was figuring out how I could achieve faster sample rates. I was constantly struggling with low sample rate outputs that would lead to my instability in hover. My original PID outputs clocked in at around 50 Hz, which is terrible. This was largely due to the signal processing of the radio frequency input via the analog read command. This function is notorious for having long execution times due to the built-in error checking logic. After a few months of research, I learned about the wonders of FreeRTOS and the remote control receiver, RMT, within the ESP32. I leveraged the built-in ESP32's RMT receiver, which didn't bog any of the CPU processing times, as this was its own dedicated receiver. As soon as I made this change, my sample rate increased from a mere 50 to almost 2,000 samples per second, an incredible achievement. For the PID plant design, since the angle set points are estimated using the complementary filter based on the gyro and accelerometer readings, this introduces a time delay that makes PID hover extremely difficult. To mitigate this, I introduced a cascaded PID loop architecture. The way this works is that the outer PID controller is the less time-critical loop. It feeds the inputs for the more time-sensitive inner loops. The trick for good hover is to process the PID hover on the gyro and accelerometer readings directly, since these are the fastest sensor response times that don't have inherent latency due to their estimation, such as the roll, pitch, and yaw estimates. But I want to be able to fly the drone via roll, pitch, and yaw commands as opposed to angular speeds. When I set the angle using my radio frequency controller, this value is processed within the inner loop. As a result, it increases the error of the outer loop, which is based on the angular velocities. As a result, the drone speeds up or down to reduce the angle error, keeping the drone's angular velocity stable. Essentially, we are prioritizing minimal angular speed differences and thus stabilizing the overall drone flight. The trade-off to this architecture is that now you have to tune 6 PID values, but the flight results are truly impressive. I set up a test rig to isolate each DOF for roll and pitch. This would enable me to estimate the initial PID parameters in a controlled fashion. After a few days of testing and tuning, I ended up with the following initial PID settings. I expect the final values to be close to these. The final PID values will be determined during actual flight testing. A quick side note about the ESP32 is that it also has 2 separate cores that can be used for parallel processing. I further leveraged FreeRTOS to set priorities on the signal processing, PID computation, and dashboard server management functions to overall improve the performance of the computations. Now that the drone performs great indoors, let's see if we can test it outdoors. To my surprise, the drone flies high. I almost flew it over the fence into someone's private property. Oh, that would have been terrible. I blame my poor piloting skills. At least I made those kids laugh. Let's try this again. Let me adjust the yaw trim. I accidentally set it too high. Whoa, the drone flipped over. That was due to too much yaw trim. I broke the motor to frame support, but I think I can still fly. Let's try it one more time before the night sets in. Wow, that is flying really nice, even if it's broken.
good.
Finally, all of my hard work has paid off. I actually accomplished what I set out to do many years
Careful on the
ago
way down.
and build my own custom drone design and flight controller.
Nice. It was a success. One broken arm ain't too bad.
Yeah, another 3D print, I guess, but not too bad.
Cool.
That is a wrap. There are items that I would love to add to this drone in the future, such as live camera feeds, barometric sensors for altitude hold, magnetometer for better heading control, GPS and real-time kinematics for waypoint and trajectory generation. But after spending a few years on this project, I can confidently say that this was a success and I'm ready for something new. The biggest lessons that this project reinforced in me was on maintaining persistence in light of setbacks, challenges, and uncertainty. This project motivated me to learn things that I didn't know and to step outside of my comfort zone. Also, it helped me strive to achieve a goal that I set out to accomplish. As engineers, we solve problems through a combination of analytical and technical skills with creative and refreshing approaches. Stay tuned as I have more videos coming soon that involve mechatronics applications in golf, boxing, robotics, mobile robots, and much more. If you have any interest or any interesting ideas that you'd like for me to attempt, please share them in the comments below. Also, if you would please support my page by subscribing, liking, and sharing this video with others, it would be greatly appreciated. I would love to hear what videos you'd like to see in the near future. Thank you and stay venturous.